Okay. So we'll be doing this our session in four different sections. So I have explained the sections. So we'll be starting on one section number one, which will be in basics of air compressor. So you are from like major of the participant in our this training program are from industry and industrial background. So they must be aware of air compressor. So all like the majority of industries use this kind of utility called as air compressor, which is used for pneumatic application, and it is widely used across all the format of industry. So we'll be reviewing the different applications of air compressor. So before that, what is air compressor? So like air compressor is an application where pressure it will generate a pressurized air, and it will be flowing from a distribution system to the desired user. So with like normal atmospheric air has some pressure, which is an ambient pressure, we can say, as a one bar. But whatever compressed air has a multiple different layer of pressures, like major industry uses are 6 bar, 7 bar. So we compress the air and send it to the user where the high pressure applications are used. So this can be widely used across very different applications. Like, so one application is an instrument ear in the chemical industry, or in pharmaceutical industry, instrument ear where operation of opening and closing of valves. So it is done by pneumatic methodology. So this is one application. Another application is like in shot blasting at automotive industry, where the surface cleaning is done by shot blasting, or that kind of application where the granules or sand blasting is done with the help of compressed air. With the help of pressure, the surfaces are cleaned, and the oil or rust particles will be removed with the help of pressurized sand particles or abrasive particles. So these are various application. So why compressed air, or why compressed air is widely used? Because it's like, we can say, it is an hazard free operation, where it is used like wise. If you use it wisely, it is an hazard free operation. Wherever there are multiple applications where electrical instruments are not allowed, so there can be compressed air instruments like pneumatic grinders, pneumatic buffing wheels can be used. It can be controlled with the help of guns or something like that. So these these are some application. And one more thing is, whenever we are generating and compressed air, so 10 to 20% of whatever electrical energy is there, it will be if we are applying 100% of electrical energy, so output of that will be just 10 to 20% in the form of compressed air. So that's why compressed air is an expensive methodology, or we can say the majority of balance 70 to 90% heat energy is converted into heat, friction, noise, such, and where in the distribution losses on all these things. So user gets only 10 to 20% of useful energy. So if we are applying, well, let's say 100, you will get 10 to 20%. So the cost of 100 will be only 10% of your compressed air. So it is an expensive methodology. Just a moment. Sorry. So compressed air is, whenever we are generating compressed air, there will be a lot of like losses. So losses will be in form of friction, then form of heat, unusable heat, which is called as a discharge air, discharge compressed air, where the compression work of compression is converted into discharge compressed air. Another is noise. So you'll be hearing some noise from the compressor. There will be friction between in the distribution piping, like in the walls, bends, and all these things. There will be some wastages also in the form of air leakages in distribution system. So all of that accounts to 70 to 80% of energy. So if you are applying 100, you will get 10 to 20. So that's why your compressed air is an costliest equipment, we can say. It is the mostly used, widely used, but is an also expensive equipment. In there is there are like in while doing multiple energy audits, uh, we have reviewed the data of multiple industries, and like in general engineering industry, your air compressor energy consumption accounts around 30 to 40% of your overall energy consumption. Such impactful equipment is air compressor in your electricity bill or in your energy consumption. In general engineering, if your energy bill is around 10 lakh rupees a month, so you will be, if you are analyzing this data, you are bifurcating that 10 lakh into multiple utilities. So you will be observing that your 3 to 4 lakh rupees worth energy is consumed by your air compressor and allied that particular air compressor dry and all these things. So that impact is of air compressor in an industry. So or if we are visiting a chemical factory or a pharmaceutical factory where processes are used, so there will be a multiple air compressors. There will be multiple air compressors that will not account 30 to 40%, but that multiple air compressor has a multiple distribution network circuits. There will be having multiple spares to account for that air compressor. So that's why your air compressor is an expensive. And majority there is an awareness of there is an awareness in industry. So how air compressor has to be used, or what are the methodologies to be used for energy saving in air compressor. So that will be doing in our last part of our session. But there is an awareness on air compressor industry. So when we are doing an air compressor or compressed air system, there are multiple terms used in air compressor. If we are reviewing a nameplate of air compressor, any nameplate of air compressor, there will be a model of air compressor, whichever make or model is that. Then there will be free air delivery in majorly it is in CFM or liter per second. So that is called as a free air delivery. So that is main term of your air compressor. So whatever the capacity, we can say capacity of compressor is established in free air delivery in CFM or NM cube per hour. So we'll be doing the FAD. What is FAD? We'll be reviewing that FAD in next part. Then there will be load pressure, there will be an unload pressure. Such terms are used in compressor. Then there will be specific energy consumption. Another term is called a specific energy consumption. It is an effect. It is a measure of an like it is an efficiency of compressor, or we can say the performance measurement criteria of an compressor, where majority of compressors are sold on this particular criteria. Like we have a lower ACC, what is kilowatt per CFM. We have a lower ACC than our competitor. So these are the some criterias which are useful in your performance assessment of air compressor. Then there is a pressure ratio term. which is
Compressors use a reciprocating and screw only.
no,
So
no.
this.
There are multiple compressor. We'll be doing type of compressors
Okay.
in next slide. So there are multiple compressors.
Okay. Yeah.
Yeah. Oh, so there is another term called as a pressure ratio, which is an a ratio for unload pressure and load pressure. Sorry, load pressure and unload pressure, which is uh, which is a main criteria for your performance of your air compressor. And your pressure is majorly compressor pressure is given in bar or kg per cm square. So these are some basic terms of air compressor. Then so these are industry-wide applications, industry-wide applications of air compressor. In like whenever you are doing the apparel industry or doing cotton industry and all these things, we'll be seeing that there will be multiple conveyors, clamping, tool powerings. So that can be used for such as air compressor application. Then in automotive industry, it will be in tool powering. Then normally there are multiple equipments like pneumatic presses are there in CNC, BMC, we use compressed air. So that is major application. In chemical industry, in control actuators is a major role of compressor. Instrument air majorly is called as an instrument air in general terms. In food industry, there are multiple applications. So these are some applications in your uh, air compressor in industrial zone. Then there are some application in non-industrial zone, like in mining industry, which has applications are pneumatic tools are there. Then pneumatic pumps are there, controls, actuators are there. In power generation, majorly auto this year compressed air is used in emission control equipment like if you are using boilers as an primary source of heat, so there will be pollution control devices such as electrostatic press filters and back filters. So they will be using air compressed air for purging of air for cleaning of that particular flue gases. So these are some applications in recreation also. We use air compressor in like if you are visiting any theme park or water park like amusement parks, so there will be stimulators and all these things, so that will be based upon your compressed air. So in general we have seen in service industries like while filling the year to your tires in nowadays in your car service centers, there are multiple pneumatic tools are used in this particular uh, by usage of compressed air. So these are some industrial and non-industrial applications of compressed air. So so you have got the basic of compressed air, where it is used, and then why it is so widely popular. So this is these are some applications.
In
Then
sewage disposal. So
sorry.
how it is used? You have mentioned here sewage disposal.
In wastewater treatment, it is used for agitation purpose. Agitation, then majorly in agitators,
STP plants.
STP plants, in agitators kind of thing.
Okay.
Blowers, root blowers are used in agitation. Wherever
Okay.
there are cleaning or like clarity of water has to be there. So these root blowers are continuously used in wastewater treatment.
Okay.
That will be in a compressed air, but is an application of compressor. Like root blowers is a type of compressor,
Right.
whichever has a low pressure, but more than your ambient pressure.
Yeah.
Yes. So we will be doing the type of compressors. What there are multiple type of compressors. Majorly, it is divided into two type of compressor on the basis of their application. Sorry, basis of their application. One is a positive displacement compressor, and another is dynamic or centrifugal compressors, dynamic air compressors. So the basic difference between both of them are like in positive displacement compressor, it reduces the volume but the increase pressure, and in dynamic or centrifugal compressors, it increases your velocity, output velocity, and by the virtue of increased output velocity, the pressure is increased. There are if you see the example of it, positive displacement compressor and dynamic air compressor, will go one by one. If we are having an example of screw compressor, which is widely used, normal screw compressor which has a 7 bar pressure. So your suction air is coming into that particular compressor, when then the screw element, in the screw element and between the screw element, the air is compressed and it reduces the volume and it increases pressure by passing through that particular screw element. So that is a virtue of positive displacement of compressor. And in centrifugal compressor, where 2000 cfm, 3000 cfm, higher air delivery is required. So it is a centrifugal compressor normally act like your centrifugal pump. So impeller is there, so it will pass the air through that impeller. It will pass on that particular impeller. It will generate more velocity on that air, and the pressure will be increased.
This CFM is same as HVAC, or this is different nomenclature?
No, in HVAC, CFM, the air quantity is defined as a like unit of air quantity is
Cubic
CFM.
feet per minute, right?
Yes, air quantity is same, but
Hmm.
in HVAC, CFM is like not different, but the terminology is different. In your compressor, CFM, both are air quantity only, but
No,
the
no. Some specific industries asking that I want this much of compressor. So
okay.
he will mention in CFM, or there is another unit.
No, it will be mentioned in CFM.
Okay, and what about the static pressure? So you have to decide it, or
Not static pressure. In compressed air, there is no static pressure. In HVAC, it is a static pressure.
okay,
Across the blower, you will be seeing static pressure. In
right,
majorly, when we are defining an air compressor, or let's say there is a case study, there is a case where if we are buying for an industry, there will be some. Let's say an example of general engineering industry where VMC, CNCs are used,
right.
or such is an example. So I do have 10 number of CNC, I do have 10 number of VMC in my plant, and then another 2 3 application of air cleaning and all these things. So I want to purchase an air compressor. So what I'll ask to manufacturer, or I'll ask to an various supplier of an air compressor. I do have particular 10 CNC, 10 VMC, where my pressure requirement is maximum pressure requirement is, let's say, 6 bar
Okay,
across CNCs or VMCs. My maximum pressure is 6 bar. I will give the specific pressure requirements of that particular CNCs and VMCs, and then general air cleaning will require 3 to 4 bar. So I'll give the pressure requirements. Another term of that particular application is air quantity requirement, which is called as air quantity, free air delivery of free air delivery is more into compressor, but for CNC it is like once we are seeing, so I do require 20 CFM across one CNC. So let's say 20 CFM across all 10 CNCs and 25 across 10 VMCs. So 20 into 10 is 200, 25 into 10 is 250. So 200 plus 250 is 450. Another cleaning application will require more 50 CFM, will be 500 CFM. And considering engineering safety or engineering margins, so we'll go by 10% or 15% more, whichever is suitable. So let's say 550 CFM is your air requirement across your plant. So my year requirement, let's say highest year requirement at the plant would be 6 bar, which is across all the equipments, 10 CNC, 10 VMC cleaning application. So it is a 6 bar. So my year requirement is 550 CFM and 6 bar.
Okay.
So
Means I
I'll
am
be
getting that 6 bar pressure at that equipment terminal.
at
Right?
equipment terminal.
Okay.
I'll require 6 bar at equipment terminal. So
Okay.
considering my requirement is 6 bar at equipment terminal, so I'll select the compressor considering your pressure drops across your circuits. Then there will
Yeah,
be a
yeah.
pressure drop across your filters. Then dryers will be there some pressure drop. There
Right.
will be another pressure drop across if we are having leakages in our line, so there
Right.
will be considering safety margin. So we'll be selecting 7 bar. Let's say
Right.
7 bar.
Right.
So whatever pressure drops is there, if we are doing an engineering, we'll calculate the pressure drop across the circuits, and we'll be selecting 6 bar to 6.5 bar or 7 bar. So our requirement would be 550 CFM at 7 bar. So this will be we will be sharing our inquiry to various suppliers. So they will be quoting on that particular 550 CFM and 7 bar. So
Hmm.
we'll be using 110 kilowatt motor. Then our ACC will be 0.11514. We'll be comparing across all these parameters. There will be technical comparison on the basis of your specific energy consumption, what type of you are using dryers you are using. It is an inbuilt dryer or an external dryer has to be fitted.
Okay.
What is the methodology of cooling of air compressor? Because it will be requiring air cooled compressor or water cooled compressor. That is one type of, if you don't have water cooled circuit in your entire factory, and supplier is quoting for water cooled, so you need to buy another cooling tower for that. So
Right.
that is an additional expense, or a cooling tower is an additional expense, because it will require soft water and all these things. So
Yes.
we'll be selecting air cooled compressor. So that is our multiple selection criteria. Another and in your HVAC, you will be having majority your requirements in TR, ton
Right.
of refrigeration. Let's say 2.2 TR is required. For that particular 2.2 2 TR delivery of removal the heat of 2 TR from your particular cubicle. So we'll be requiring certain airflow. So we'll
Right.
be requiring 1200, 1400 CFM. So that 1400 CFM is not much critical parameter in HVAC, but in 1400 CFM is much critical parameter in air compressor.
Right, sir. Right. Thank you.
Yeah. So these are some basic differences across. Like you will be seeing, you will be like in kcal per hour, heat rejection will be in kcal per hour. That kcal per hour will be converted in TR in for HVAC, but kcal per hour will be directly used for boiler, or
Okay.
kcal per hour will be converted in ton of boiling or heating. Then kcal per hour is used in thermic fluid heater as such as kcal per hour. So those units can be differently applied to different utilities.
Right.
Yes,
So in compressor technology, we are having the inverter compressors or like similar that technology.
no. That entire HVAC part is different compressors. Those are
Okay.
different compressors. They are used for your chilling, cooling applications. Those are different compressors. These are air compressors are different compressors.
No, considering the power consumption, so can we have an option of VFD connectivity or like that?
Yeah, variable drives are there. Whatever you are saying, inverter based or inverter, those terminologies are for your split ACs or VRV kind of thing. Variable refrigerants are used. So these are the major different. So
Okay.
you have a variable drive in air compressors. You can use the variable drive in air compressor,
Okay.
but that variable drive does not means that there will be a refrigerant or the variable refrigerant or such terminology. So that particular variable drive will control your speed of compressor.
Okay.
control the speed of motor.
Right.
So that is different. So whenever we are going through our energy saving measures on high cost methodologies, high cost measures, we'll be reviewing the use of variable drive in compressor.
Okay, sir. Yeah.
Nowadays multiple there is multiple terms across coined across variable drive, like variable VFD is there,
Right.
VSD is there. So multiple terms are coined across drives.
Yeah, even in for the screw chillers,
uh,
they are having magnetic bearings and like that for
that
sustainability and power
Yes,
savings.
maglev chillers are like the whatever magnetic chillers or maglev chillers are used for your lower specific energy consumption.
Yes, yes.
Yes. So
Yeah.
the entire variable drive would be same, but its application of variable drive is different. Will be different.
Okay, sir. Yeah.
Yeah.
Thank you.
So where we were like in the different form of like in the different type of compressor, there are two major differentiation. One is a positive displacement. One is a dynamic type of compressors. Where there is a main difference of in positive displacement, you reduce the volume, increase the pressure. In centrifugal compressors, you increase the velocity of air and increase in pressure. So you compare your centrifugal compressor to centrifugal pump. So same kind of methodology is used in centrifugal compressors. Like impeller will be there, and then there will be radial or axial flow. So all the same application is in centrifugal compressor. And in your positive displacement, there are multiple bifurcation again. One is type of air compressor is a reciprocating air compressor. Majority the older industry or many process industry use reciprocating air compressor due to requirement of higher pressure, due to requirement of like they can be useful for multi-stage or delivering the high pressure. The reciprocating compressors are used. And in another is your rotary air compressors. So that rotary air compressors are further divided into roots blower and screw compressors. So this screw compressor is common across your engineering industry, or
Right.
screw compressor is common nowadays, common due to the non-maintenance or low maintenance activity that uses air. Like likewise, we took the example that we don't have cooling tower in our plant. How to cool that particular air compressor? So we will go for air cooled screw compressor. So that's why these screw compressors are more frequently used. And then there is a efficiency or specific energy consumption, that particular screw compressor are more efficient, and all these things are coined nowadays. So reciprocating compressors are further like that particular in the reciprocating compressor, your compressor capacity is directly proportional to speed of compressor. That such small will be used in your MCQs or uh, kind of one mark questions. So what is like which compressors used directly proportional to this capacity is directly proportional to speed of compressor. So that reciprocating compressor, if we increase the speed of compressor, your capacity will enhance.
Okay. So we have a range of CFM as per these compressors.
Yeah, range of CFM, like if we are having that particular, if we are majorly this particular.
You are not audible, sir.
Hello, I'm
Yeah.
audible? Yeah.
Yeah. No.
Yeah. So that particular type of compressors are, if we are having different capacities. So roots blower, majorly your pressure in the root blower is around 0.1 to 1.1 compressor. 1.1 bar roots blower are majorly used. Those are low pressure application in agitation, then in water cleaning. Those roots blower are majorly used. Then uh, those can deliver your zero point 0.1, 1.1, 1.2 pressure. Then those are roots blower are majorly single stage compressors. Then another is reciprocating compressors. In reciprocating compressor, there are further classification. For that further classification, which will be depends on in reciprocating compressor, there will be single stage or multi-stage compressor, where a single stage is used, where your air that particular air pressure requirement is on lower side. When multi-stage are used, where your pressure requirements on a higher side used, like 20 bar is requirement, 30 bar is requirement for your multiple applications. So that will be use multi-stage compressors, multi-stage reciprocating compressor. For 7 bar, it will be using single or two stage compressors. Then there are air cooled and water cooled reciprocating compressors, based upon the cooling methodology of your discharge, cooling methodology of your compressor, that will be classified as air cooled and water cooled. Then in screw compressors, majorly in screw compressor, there are pressure ranges across industries, and single stage screw compressor, wherever you can deliver up to 1000 cfm, 700, 800 cfm, uh, and your pressure range is across 6 bar to 13 bar. You can use single stage compressor. Those further can be water cooled or air cooled. Then in screw compressor also, there can be stages of uh, multiple stages of particular screws. Like one can deliver 6 bar, then 6 bar here can be are further enhanced or compressed to 12 bar, 13 bar. That will be in two-stage compressor. And another compressor is dynamic air compressor, which is centrifugal compressor. This centrifugal air compressor is majorly used where your application, sorry, where your quantity of air is huge, in like major like major automobile industry, where multiple shops are there, like multiple paint shops are there, multiple fabrication, multiple stamping units are there, or press shops are there. So there we can use centrifugal compressors. So where you are, and it can be centrally placed, and the air ring main or air distribution network is there. So where there we can use centrifugal compressor. So in multiple compressor type, there can be few multiple choice questions, or say one liner, two liner questions, like whichever is efficient compressor in uh, whichever is the efficient compressor in reciprocating, single stage compressor is efficient or multi stage is efficient. In that particular, multi stage will be more efficient due to better performance enhancement, or better like the multi-stage. In multi-stage two-stage compressor, you will be having one stage lower has to do less compression work, and then another stage has to do less compression work. So there will be lower pressure ratio. Like if I have to increase the pressure from 1 to 4 bar and 4 to 12 bar, so there I'll be using two-stage compressor. So 1 to 4 will be done in first stage, and say 4 to 12 will be done in second stage. So my pressure ratios are on lower side. So I'll be doing less compression work, and it will be more efficient. But in single stage compressor, I have to do 1 to 12. So my pressure ratios are on higher side. So there will be uh, more work has to be do for the compressor, and higher will be motor power or input power will be there. So your single stage compressors are less efficient than multi-stage compressors.
So how the efficiency is measured for these compressors?
So there are two kind of efficiency. One is your isothermal efficiency, and another is your volumetric efficiency. So they are
And which standards are followed for these compressors?
there are no standards like in if we are reflecting efficiency in like motor efficiency or referring the motor efficiency or pump efficiency kind of standards or formula kind of thing. So those compressors are not based like selected based upon that particular efficiency part. Those are selected on performance part.
No, no. Suppose we are going for lead well like IGBC certifications
Mhm.
for green building. So in that case, what are the standards for these air compressors?
Need to check that.
Okay.
No, need to check that on that particular part.
Yeah.
But majorly your air compressors are selected based upon your specific power consumption or specific energy consumption. Like
Okay.
kW per CFM is major criteria selection. So and then another concept is that which uh, which air compressor are more efficient, air cooled or water cooled. So water cooled are more efficient in term of like water in water cooled, you can dissipate it more heat, and the water can carry more heat than your air, and the you will be requiring more amount of air to be circulated for air cooled compressors than your water cooled compressor. They are in multi-stage compressor, there are multiple stages. So I'll be doing that in what are the components of your compressor. So these are some type of compressor used in.
And
Sorry,
power consumption for the air compressor depends on this CFM capacity or pressure. Yeah, both.
both
Okay.
on the both side. If we are selecting, let's say 500 CFM is your air requirement and your pressure requirement is 7 bar, will be mota moti, you will be having
You are
110
not
to
audible.
100. Hello,
Yeah, yeah.
I'm audible.
Yeah, yeah. Audible now.
So find if you are having a requirement of 500 CFM air delivery at 7 bar, we will be
Okay.
having muti 110 kilowatt, 90 kilowatt to 110 kilowatt motor input
Okay.
power. But if you are having 500 CFM requirement at 13 bar, we will be having more requirement. The motor input capacity will be on 150, more than 150.
Okay.
That depends on your pressure ratio.
Yeah.
So in entire air compressor, what is your pressure ratio? That is the main criteria.
Okay.
So if you are having if you are working air compressor, working pressure of air compressor is 4 bar. So you'll be having pressure ratio of, let's say, one is your ambient air pressure and 4 is your delivery pressure. So you'll be having 4 as an pressure ratio.
Right.
You are having 7, so it will be 7 as a pressure ratio. So 4, the compressor which has a 4 as a pressure ratio will be doing lower work.
Right.
It and which compressor has a 7 pressure ratio, it will be doing more. It has to do more work.
Okay.
The air, if you are increasing your air pressure in single stage compressor, the higher the pressure, your input power will be on a higher side for your same requirement, same air delivery requirement. And if you are use uh, how both are critical uh, for your motor selection, like if you are having requirement of 500 CFM, we will be having at 7 bar, we will be having 100 kilowatt motor. And if you are having 100,000 CFM or 1000 CFM requirement at 7 bar. Pressure is same in both the cases. Pressure ratio would be same in both the cases, but your motor power is going to be on 150 kilowatt.
Okay.
So both the criteria are main selection criteria in the air compressor. In multi-stage compressor, so if you are using two-stage compressor and you are doing you are producing air at 12 bar, so you'll be setting those two stages as 1 to 6 and 6 to 12. So you'll be having 6 as a pressure ratio in both the stages. But if you are doing in single stage 1 to 12, it will be a higher pressure ratio. So
Right.
whatever pressure ratio is there, your performance is going to be on higher side. If lower pressure ratio, performance is on higher side.
Okay.
So there are these are the type of your air compressors, such as reciprocating air compressor, centrifugal air compressor, rotary air compressors. These are application based. We can say application based air compressor type, and the methodology of uh, operation is different in the both the compressors.
Yeah. Thank you.
Yeah. So these are the type of air compressors. Then these pressure ratios can be different for different compressors. If you can't use single stage screw beyond 13 bar because the economical and ergonomics can be on higher side. That is the different pressure ratios are there in this according to capacity, and pressure will be there. This cannot be used in your MCQs, but that particular which is has a higher energy consumption, air cooled or water cooled, or which has better efficiency, that can be used in your single mark questions. Then these are the some major equipments in your air compressor, like compressed air system components. So these are two air compressors are used in this particular image. So this is an entire picture of your any industry where there is application, there is a compressor side and distribution side is shown in this particular picture. So this is, I'll use the pointer. So this is your air compressor.
Hello.
Hello, am I audible or not?
Yes, sir, you are audible.
Yeah, yeah, audible, audible.
Okay. So these are two air compressor used in this picture. So we'll go one by one. So these are yes. So these are different equipments are used in air compressor. One is this is your induction motor is used in air compressor. This is your after coolant or lubricant cooler. Then there is a control panel. So this is compressor end. This is lubricant or air separator. Then this is your distribution system. It will be directly this particular headers are connected in one, both the compressors are connected in single header that will be going to your dryer. This is your air dryer. Then there is a air filter, and after that air filter the air goes in receiver. So that air receiver will be circulating your entire air to the plant. So these are different applications. So of air compressor. This is one another receiver used. This is filter regulator FRL unit. We see nearby many high-end equipment or high-end machines like CNC, BMC has FRL units. So this is condensate drain or moisture separation from air is used in your receiver. So the moisture will settle down and then condensate or moisture will be thrown out of your air system with the help of manual methodology or automatic timer based condensate drain methodology. So these are some uh, different equipments. This air inlet filter, what is the use of your air inlet filter? So when there are inlet air filters are used, wherever whatever dust particles or these are present in your air ambient air, it will prevent that dust particles to flow into direct air compressor, because it will damage your walls and cylinders and all these things in your entire distribution network. So the air filters are provided, and that particular after that filtering the air passes to the in compressor or in compressor. So that will be next component will be this after cooler or lubricant cooler. There are multiple coolers in air compressor. One is your after cooler would be there, then intercoolers are there. Then there will be lubricant oil coolers are there. There are multiple coolers in air compressor. So interstage coolers are like for that particular in the both the stages there are coolers where the air temperature is drastically taken down to taken down. If we are compressing air temperature is gonna rise. So that particular temperature needs to be on the lower side to reduce the work of compression. So that intercooler are used in between the stages. So that will be an air cooled intercooler or water cooled intercooler. Then there are aftercooler or moisture separators. Aftercoolers are more called as moisture separators also. So that particular aftercoolers are used where that particular compressed air has some part of moisture, because we don't have any control on ambient air. Like if there are during your normal days of summer, so there will be less humidity in the air. But during your monsoon season, the air will be more humid. So you don't have any control on ambient air. So so air will be having moistures. So it will be carrying through that particular compressor. So that has to be separated, because if you can't allow moisture or water to be in your system, your compressed air system, because it will be damaging your distribution network. It will be causing rust to a distribution network, or uh, causing the uh, causing the harm to the particular equipment whichever you are using as application of compressed air. So that we cannot allow water to be flown in system, or in the instrument here there has to be no water at all in the compressed air network. So the major load will be on after coolers, then air dryers will be there. So after cooler, the work of after cooler and air dryer is to remove the from your moisture from your system.
So, what is the recommended humidity in compressor? It's a standard or it changes from industry to industry?
No, the like it does not changes. It does not have any recommended measure, or it does not have any recommended number. So if for the instrument here, you don't require a single droplet to be in near to that particular instrument here.
Okay.
But but for the cleaning purpose, you can have water, but typically the water should not flow in your distribution network.
Okay.
So it does not have any recommended number, but it does like it should recommended number is zero, ideal. It should be an
Okay.
ideal, but there is no situation such as ideal. But it depends upon the user.
Okay. Yeah.
So user wants to use for cleaning purpose, so that he will not bother more.
Right.
The user wants to do it for agitation purpose, it will not bother. But
Yeah.
user
In
wants,
STP, there will not be any restriction.
no, not STP. In general engineering industry, the people are not more focused on dryer.
Right.
They do have a dryers, but
Mm-hmm.
not that oil free, air water free dryers kind of thing, or oil free compressors will not be using. But in pharma industry, you need to have both oil free compressor, and then dryers has to be efficient, so that they will be more in need of compression dryers, and all these things will be using for
Right.
that particular moisture need not to be flowing through the system, because any part of moisture in pressurized system, it will cause corrosion more. In steam system also will be will not carrying wet steam, or will be requiring dry saturated steam at your user end.
Right.
It will create more uh, heat transfer more efficiently than wet steam.
Yeah. Right.
So that are the some like phenomena. So then there is a another moisture drain traps are used, or condensate drain trap. Like these are the condensate drain trap or the receiver in distribution system. There can be a moisture drain traps used in the system. So these condensate drain trap are nowadays timer based, or moisture based condensate drain traps are used. Then this is a receiver. Receivers are mostly used for your system where you want to create an buffer. You don't want to you don't want to pass an pulsating effect, or you don't want to pass uh, that particular effect, load unload pressures to the user. So you want to create a buffer, so you place receivers here receiver in the system. So if you are visiting a large plants where they have a bigger size of networks, so they do have multiple receivers, so they don't want to create an volumetric shock to the user. If your user have a your requirement, higher requirement, so they will create an additional buffer to that particular. So this kind of application like volumetric shocks and all this used like volumetric shocks or volumetric surges are there in short blasting kind of thing, or there is a CO2 cleaning kind of thing where direct purging of air is there. So that they need an additional receivers in particular system. So then there is a dryer. So main component of your system is dryer. So to remove the moisture from your entire system, dryers are majorly used. Then there is a air filter. So whatever any hazardous particle or any particle is passed to the system, so they will remove that particular in the air filter. So this is your ideal typical compressed air system in industry. So these are some uh, equipments, or these are some components are in the compressed air system. So before going to the efficiency evaluation or performance evaluation, if there are any doubts in till now.
No, sir, no.
Okay. So further part of your module is evaluation of performances. So what is free air delivery? So free air delivery is an capacity of compressor. In typical language is the capacity of compressor. But what does this mean? So this is an flow of gas compressed at inlet of compressor and at your desired pressure. So majorly FAD is at inlet of compressor inlet. So that can be used is in your MCQ while we were doing our exam. So that MCQ was asked to us. So FAD is at outlet of compressor or inlet of compressor. So it is FAD is at inlet of compressor. And this FAD varies at due with multiple parameters such as your FAD varies at temperature, your FAD varies with pressure. So these are some parameters affecting the free air delivery. Then there is a term called as an efficiency of compressor. So the efficiency of compressor is coined in two type of efficiencies. Multiple efficiencies are calculated, but your main efficiencies, one is isothermal efficiency and another efficiency is volumetric efficiency. But apart from the efficiency, your main practical term to evaluate the performance is uh, specific energy consumption of compressor. So, what is the isothermal efficiency means? Isothermal efficiency is a ratio between isothermal power and actual measured input power. So, how does isothermal power calculate? Isothermal power it depends upon your mainly your pressure ratio and volume of free air delivery. So that isothermal power is calculated such as input pressure or absolute intake pressure, whatever absolute intake pressure, major times, your absolute intake pressure is an ambient pressure. So absolute intake pressure into free air delivery into your pressure ratio, log of pressure ratios divided by 36.57. So your pressure ratio is, let's say, 7 bar is your desired pressure and your input pressure is 1 bar. So your pressure ratio is 7. So P1 into Q1 into log of 7 by 36 by 7. And your input power is, let's say, 30. So that particular ratio is called as isothermal efficiency. You will be having some numericals on that calculate the isothermal efficiency. You will be given all the parameters. In numerical section, we'll see those numericals. Then another uh, this particular isothermal efficiency does not calculate your entire efficiency part. So there is another efficiency is called as a volumetric efficiency. So volumetric efficiency does not need your input power or measurement of power kind of thing. So in volumetric efficiency, what is the displacement of compressor? What is the work done to be compressor has to be do? So that is calculated. So free air delivery is given in your compressor, let's say 100 CFM, and divided by compressor displacement. Compressor displacement is compressor work done. So compressor displacement is calculated as pi by 4 d square into L into S into X into N number of cylinders. So D is your cylinder bore. So that formulas you need to go through your like book once, but majorly your isothermal efficiency is asked in your numericals, 5 mark numericals, not the volumetric efficiency. Many times volumetric efficiencies are not asked, or if asked, they will be providing your compressor displacement formula or such thing. So they will be providing that particular formula because it is hard to remember, and there are multiple terms, like they will be having the diameter of cylinder bore. What is cylinder bore? Then cylinder stroke has to be there. Then compressor speed. What was the compressor speed in RPM? Then there is a single stage compressor or double acting cylinder or single acting cylinder is there. Then number of cylinders has to be there. So this formula can be given in your question if it is asked. So these are the two type of efficiencies while calculating the performance of your air compressor. But I'm impact more giving impact on your specific energy consumption because it is a majorly a widely used terminology in energy audit, energy conservation opportunities. So this is compressor SSE is majorly used. After your exam, you'll be using more. What is your specific energy consumption of compressor or savings in a compressor? That particular term is used. Then there are methodologies of methodologies of evaluation at site. So there are two methodologies, two tests to be conducted during your assessment. One can be free air delivery test, and another is a leakage test. So during your free air delivery, what is your formula for the calculating the free air delivery? P2 minus P1 divided by PA is ambient pressure into volume of receiver into divided by time to fill. So I'll explain this particular one by one. The procedure of free air delivery or procedure to calculate the free air delivery. Suppose you are having this system. Suppose you are having this system and you need to calculate the free air delivery of this particular compressor. So assume that we are on the field and we need to calculate the free air delivery. So that particular the calculation is such as, so assume your final pressure is 7 bar. Your input pressure is, let's say, 1 bar, and absolute pressure is 1.03, which is an ambient pressure. So 1 bar is your P1, your final pressure is 7 bar, ambient pressure is 1.03 bar. You need to calculate the volume of this distribution network. Assume there is only one compressor. This compressor is not in the system, and this receiver is not in the system. So this is the only system directly passing to the user end. So you need to calculate the volume of this particular pipeline, distribution pipeline. How to conduct this test in practical approach or in practical methodology? So you need to stop the usage of compressed air. So if there is a butterfly wall or there is a wall to the output of your receiver, you need to shut those walls. So your distribution is not in place or not in use right now. So there is no usage from the compressor. So you need to fill this air receiver. So if the air receiver was in place, so you need to drain that air receiver first. So if you are draining, so you can drain from this particular condensate pipe, or there are some additional source of additional discharge points are given to the many receivers that we can drain those from this. So you need to ideally empty the receiver. So all water will be thrown out, all air can be thrown out from the receiver. So only this piping network and the receiver is in place. So you need to calculate the what is an approximate storage volume of this piping or and the storage volume of that particular receiver. that storage volume will be given on your receiver tank, and you can calculate the approximate storage volume from the this circuit. So we have emptied the receiver right now. So we after emptying the receiver, we need to start the compressor. So right now compressor pressure would be, let's say, 1 bar. We have emptied the receiver. We have uh, we have stopped the compressor first and then emptied the receiver. So it can be 0 bar or 1 bar, near to 1 bar, if there is some error in the network. So we assume it is a 0 bar right now. We assume it is 0 bar. So your starting pressure is 0 bar. So you need to start the compressor. After the starting the compressor, you need to record the time. So you start the stopwatch while starting the compressor. So after your load cycle starts, 4 5 seconds, your load cycle starts. So compressor actually start to deliver the compressed air to the receiver. So to gain that final 7 bar, what is time taken for that particular compressor? It's called as pump up time. So which is T, T in the formula. So which is called as a pump up time, or time taken to fill that particular compressor receiver. So in that particular in this particular uh, scenario, we know the initial pressure, we know final pressure, we know distribution volume. Let's assume your distribution volume is 10 meter, receiver is 10 meter cube, and this is your 1 meter cube distribution volume. So your total volume is 11 meter cube, and you 7 is your final pressure, 0 is your starting pressure, absolute pressure is 1.03, 7 minus 0 divided by 1.03 into 11 is your volume, and time taken was 5 minutes. So 7 into 11 divided by 5 into 1.03. So will be getting around 14 to 14.5 as your delivery FAD. So which will be in meter cube per minute. This is
So
your pump up test formula or pump up test methodology.
for pressure balancing, so PIBCV walls are used, or which type of walls are these for the
For
line pressure and all this?
sorry, I
For
didn't get it.
hello,
I didn't get it, sir.
for pressure, you are saying that if the pressure drops,
Uh,
so any type of signaling system there, or PIBC walls are used?
that can be normal pressure gauges.
Okay,
That can be normal pressure gauges which has particular pressure range. The
okay,
all the compressed air has a normal pressure gauges. Not the some pressure transmitters are there, which can display pressures on compressor display, or HMI pressure transmitters are there. Then there
okay.
are normal digital or analog pressure gauges are used in system.
Yeah, that's fine.
Yeah, this is the methodology of doing free air delivery test, or which is called as a pump up test during your energy audit. So this can be a 5 mark numerical, whenever you will be given all this data in the your exam. So you can calculate free air delivery of a compressor. During free discussion of free air delivery, we discussed that free air delivery depends on your temperatures. So if your input like there can be the effect of temperature on your free air delivery. If your ambient temperature is on higher side, your higher side from your test conditions or standard operating conditions, you will be seeing that your FAD is on lower side. So FAD has a correction factor. If your let's say standard operating temperature is 35 degrees Celsius, but right now your input air temperature is around 45 degrees Celsius. So there is a rise of 10 degrees Celsius. So there is a FAD correction. Whatever formula is of FAD is there, P2 minus P1 upon P0 into V by T, there will be an additional parameter which is 273 plus T1 divided by 273 plus T2. So T1 will be in standard operating temperature and T2 is your normal temperature. So 270 to 73 are 1 degree and Kelvin this thing, but that can be FAD is corrected such as like if your compressor placement is so bad that you have placed compressor in near to your let's say foundry or near to your furnace, so where ambient air temperature is on higher side, where the fumes are passing or air is on hotter side in on that particular zone, so you'll be getting that higher temperature for that input air, and FAD can be affected on that particular. So your power consumption is on higher side. So the optimum placement is also important in the compressor section. So FAD has a correction factor. During your normal assessment during energy audit, you can uh, you can apply those correction factors for the compressor. Then there is a second stage to evaluate the compressor, is which is called as leakage test of compressor. So leakage test, let's assume the same system. So there we have isolated the wall from air receiver. Right now, if we open that particular wall and allow the air to pass to various distribution system, user can use the air. And what is leakages in compressed air system? So leakages are misuse, or we can say drain points of our energy. We are sending some we are carrying one bottle of water right now, and that particular bottle water has one hole to the say, bottle, and you will be carrying 1 liter of water from your home to office, and that particular bottle has a hole. What- while going to your office, your bottle is empty, or half of the water is spilled out of your bottle. So your 50% is 50% is directly misused or wasted in your leakages. So such wastages are in general your industry. Such wastages are there in distribution system, in near to your machine, in the main header. There are multiple there are multiple leakages can be observed. So those can range to 40-50% also. In general engineering industry, average uh, leakage percentage around 20 to 20% or 20 to 30% in medium and small scale industries. So those on a higher side because they don't have such trained manpower to isolate those leakage or calculate those correct those leakages and all these things. So there can be on a higher side. So leakages are waste of energy. So how to calculate those leakages in your system? So what is the practical methodology to calculate this is leakages in system? Suppose this is your compressor, you have receiver in the system, and you are flowing the compressed air to the distribution network. You need to stop your actual applications. Let's say there are two CNC machines these operators are operating. So you need to stop the CNC machine operation. You need to put our all operations in idle condition. So there can be leakages. There will be leakages which will be draining your compressed air. So all the air will be passing through these leakages. Let's say here is one leakage, here is one leakage, here is one leakage. So all your compressed air will be passing through these leakages. So you need to run compressor to survive those leakages or maintain the pressure in your system. So compressor doesn't understand if there are leakages or there are actual usages. So that understand only I am at low pressure. I need to start the pressure. So there are two parameters. One is your load pressure. One is your unload pressure. So majority load pressure and unload pressure are let's say there is one compressor which has a load pressure as 7 bar, means this is an actual delivery pressure, and 6 bar is your unload pressure, or sorry, 7 bar is your actual pressure which is an unload pressure, and 6 bar is your load pressure. So we need to set our compressor between 6 to 7 bar. So if the pressure in the system drops to 5.5, compressor will start. But if your usages are on higher side, it will drop to 5.5. But no, in normal condition, the pressure in the zone compressor or actually operates 6 to 7 bar. So if your pressure is 6.1 bar, so compressor will sense that I am not in good condition, or I am not in uh, actual requirement condition. So I'll start my work of compression. I'll deliver the required pressure. So it will generate 7 bar and deliver those. So if it is drained by your leakages, compressor doesn't understand. It is a waste. So how to calculate that? We have put the actual operations in idle. So your you need to start your stopwatch again when there is a load cycle starts. Let's say at 6 bar load cycle starts. You need to start your timer, and what at whatever time 7 bar achieves, will compressor will be in unload cycle. So you need to do it again. So you need to measure the type of time for load, time for unload. So 7 bar it will start to unload. At 6 bar it start to load. So you need to measure load and unload timings. So let's say 10 seconds are used for load cycle to reach from 6 bar to 7 bar. 10 seconds are used, and from 7 bar to 6 bar again unload cycle, 1 minute is consumed. So 10 seconds and 60 seconds. So 10 second is your load cycle, 60 second is your unload cycle while leakages. So 10 is your loads, 10 second is your load cycle, 60 second is your unload cycle. So leakages in the system are, formula is load cycle time divided by load cycle time plus unload cycle time into 100, means percentage. So your 10 divided by 10 plus 60. So your 10 divided by 70. So 1 by 7 is around 13-14. So 13-14 percentage there are leakages in your system, because we don't have operations right now. We don't have any operating machine right now. So your entire that particular energy is used to deliver only leakages in the system. So let's say 100 CFM compressor and you have a 13% leakages. So 100 into 13% means 13 CFM during your operation, 13 CFM air goes to leakages only. And if your compressor has a 0.15, or let's say 0.20 for better calculation, 0.20 as your specific energy consumption. So 0.20 into 13 means मोटामोटी 2.6 kilowatt to your leakages. So during your operation, 2.6 kilowatt of energy is circulating, is using for your leakages. So this is methodology to calculate leakages. So these are some practical methodologies to calculate free air delivery. Then there is to calculate leakage test in your working plant. So these are some methodologies used in compressed air during assessment of compressed air or compressed air system.
Sir, what is the use of calculating the FAD? What we are concluding based upon the value we get from the FAD?
So after FAD calculation, so what is the duration factor of your compressor? We can actually get that duration factor.
Okay, but I mean we have to compare it to the standard FAD of the compressor and what is
Yes,
the deterioration over the period of usage. So that comparison will help us to conclude how much wear and tear and internal leak, I mean, wear is there, right?
you're right. And you can actually from that FAD, you can actually calculate the specific energy consumption, actual specific energy consumption. You can measure your power. Let's say when there is a 100 CFM compressor and 15 kilowatt, 11 kilowatt or 15 kilowatt motor is there. So 11 divided by 100 is your actual ACC. For better calculation, we understand 15 divided by 100. So let's say what is number around point just about 0.15 divided by 100 is your 0.15 is your 15 kilowatt motor and 100 CFM compressor is there. So 0.15 kilowatt per CFM is your specific energy consumption. But during your free air delivery test, you got to know that your compressor is delivering 80 CFM only, and your consumption of power is around 15 kilowatt only, but your delivery is reduced. So your specific energy consumption goes to 0.1875. So from 0.15 to 0.1875, will be having loss of energy. So 0.0375 kilowatt per CFM. If you are delivering 80 CFM at this, so 3 kilowatt is wasted.
Okay.
So this ACC is majorly used for to understand you to understand the deterioration factor, to understand the existing specific energy consumption, to understand why our compressors are not delivering actual pressure. If you are like in multiple during your energy audit in your energy auditing journey, you will be listening to multiple complaints like we don't get pressure our end, we don't get pressure at our machine, we don't get enough pressure, we like our extreme last machine does not operate due to lower pressure. So such complaints you can hear from your clients or multiple industries. So for that evaluation, you need to understand what is actually actual delivery. So FADs are calculated.
Okay, sir. Understood.
Yes. So these are two actual calculation methodologies of air compressor performances. Then energy saving measures. We'll go to third one is energy saving measures. Prior to going that, we'll go what are the efficient operations of compressed air or efficient. We can say how better uh, compressed air can be managed. So compressed air is dependent majorly on your input conditions. So your input condition means your ambient air. So first primary thing is your location of compressor. If you are placing your compressor near to your furnace, near to your cooling tower, you are in disaster mode, because you are not allowing normal ambient air to pass to your compressor. You are you are in near to your foundry, your intake air temperature is on higher side. Near to your cooling tower, your humidity is there, humidity of humid water can be there, or temperature can be ambient air can be humid due to operation of cooling tower, or any compressor is placed in isolated room where your exhaust of compressor in air cooled compressor, majorly in air cooled compressor, your exhaust of air is not passed through the duct, or outside the room is not passed, and its particular circulates to that particular room only. You are in disaster mode. So your pressure, your location of compressor is critical. You need to think of good air quality, dust free environment at lower temperature side. Your performance can be further optimized, not optimized, but can be ideal, we can say, at a good condition. So your cool air intake is most important. If you are allowing compressed air to uh, have a have ambient air to your compressor, it will deliver a good FAD. Just a moment, allow me. So you sorry, if you are allowing cool air to get as an intake to the compressor, you are allowing to perform compressor at desired conditions or at standard conditions. But if there is a thumb rule, if you increase your intake air temperature by 4 degrees Celsius, your specific energy consumption goes tossed by or increased by 1%. That is that can be performance deterioration over the temperature. You can provide cool air, but cool air to the compressor, but you need to take that particular pressure drop. Then ducts should be there. Duct should be good. Your humidity should be normal. Air conditioned air can be passed, but you need to see the economics, and all this calculation has to be do during this particular placement of compressor. Then there should be industry intake. We during our equipment list, we see the air filter. For that air filter, the purpose of air filter is not to pass the dust to the compressor, but if we see many air compressor filters, those are choked air compressor filter. Those are not regularly maintained. So your pressure drop will be there. For you are creating barrier between air and to air to pass air to pass. So you are allowing more work has to be do to suck that air. So that particular filters need to be regularly maintained, or dust-free environment has to be there.
These filters are PM10 or PM2.5?
No, those are regular filters. PM10
Pre-filters.
pre-filters.
Okay.
PM2, PM2.5, PM10 are majorly in HVAC
Okay.
for to have a comfort air conditioning kind of thing. Those filters can be used.
Okay.
PM2.5, PM10 filters has a more pressure drop, and during your compressor or compressed air system, your pressure drop means your input power is on higher side.
So what is the material for these filters?
Normal filters. Those are normal filters used.
Okay.
Those are pre-filters, but we need to clean those pre-filters.
Media is a paper filters.
Sorry.
Mostly the filters used as a paper media, which is pre-filter and post-filters. And suction, I think we have this, again, there is also paper filters.
So these are cleanable, or you have to just remove once choked?
Those are cleanable also, or you can remove and it can replace.
Okay.
So pressure drop across your compressor acts in a barrier as a barrier. If you are allowing more pressure drop to be there in system, your energy consumption will be on a higher side. So for the thumb rule is like that 250 mmWc you are allowing more pressure drop will be increasing 2% of air energy consumption. Then there is a dry air intake. Like dry air intake, we are seeing the example. If you are placing your compressor near to cooling tower, you are allowing humid air to pass. So your moisture can be carried over to the system. So that will be hazard or hazardous system. Then there is a elevation. Elevation in not like the elevation from sea level is also matters to that particular free air delivery, because that particular on the higher altitude your air is on your energy consumption is more. If you see the same compressor in let's say in Pune, in Mumbai, and on higher altitude like northern states, so your same compressor gives different performance parameters. Like 15 kilowatt 100 cfm at Mumbai will perform differently due to this ambient condition, like humid condition would be there. Sea level is it's near to sea level, but it's a humid condition, so your performance will be different. At Pune, it will be different performance. At north state like Delhi, it will be different performance. So those location also matters to the particular compressor. Due to that, depends on these four parameters are more important: temperature, then location, then pressure drops, and all these things can be matter to the system. Then cooling water circuit means there are, if we have seen that the compressors can be air cooled compressor, then it can be water cooled compressor. During your air cooled compressor, your discharge air should be the discharge air has to be thrown out of that particular compressed air, and your normal air has to be circulated, and that particular discharge air should be to your near to your 60-70 degrees Celsius, whatever the compressor discharge temperature at that particular pressure, 60-70 degrees Celsius will be there. But in cooling water circuit, sorry, in water cooled water cooled compressor, your entire rejection rejected heat is going to the circulating water, which is passed to cooling tower or passed to chiller. But majorly cooling water is given in compressors.
For air-cooled compressors, can we connect the de-superheater for hot water generation?
Yeah, we can connect,
Okay.
but we can't. But we can't like reuse the air, hot air, discharge air, that particular energy from discharge air. We can use the energy from your oil cooler and all these things.
Okay. So
So
means hot air, we have to just leave it in the air.
yeah, your hot air temperature will be down by if you are using waste heat recovery medium.
Okay. Like HRW and that recovery wheel.
Not recovery will, not not in the flue gas or something like that parameter, but your oil temperature should be lower. Your compressor work will be on the lower side, so your discharge temperature is automatically on the lower side.
Okay. Yeah.
Yeah. This is one of the energy saving methodology where bigger size compressor are used, 90 kilowatt compressors are used, 100 kilowatt compressors are used. That hot water can be generated through the compressors. So majorly in water cooled compressor, your intercoolers and aftercoolers are connected to your cooling water circuit. And if we are allowing that particular heat recovery from that, we directly connect to heat exchanger, and then hot water can be particular generated through this particular circuit. Then intercoolers and aftercoolers are also heat exchangers. So that particular intercoolers and aftercooler has to be maintained, such as your water quality has to be at good level. Your cooling water circuit should be that particular cooling water temperature has to be on the lower side. So your cooling tower needs to be well. So that particular are interlinked. So if your performance of intercooler and aftercooler is poor, so your power consumption would be on a higher side, because your uh, intercooler for two or three, four, let's say four stage compressor is used. In every stage there is an intercooler. So your if initial temperature at first stage should be your output input at second stage temperature. It's an ideal condition. So if your initial temperature was for 35, say at second stage, after the work done, your discharge here has to be at 35 degrees Celsius. So that effectiveness has to be there in intercooler. So that much good water, good cooling tower performance has to be there in your system. And if you are we are allowing bad intercooler performance, then your power consumption is on the toss and it goes on higher side. So there are cooling water requirements, different cooling water requirements in your system. Like at, let's say, for 100 CFM, there is a different water requirement, and that has to be calculated during, and that has to be passed to the uh, particular compressor that has to be given. Uh, this is a major disaster or major design error in the compressed air system. Like there is a cooling tower available in nearby your vicinity, and you are purchasing, means in chemical and pharma and such industry, this kind of mistakes happen. Like if we are having a cooling tower and which is a chiller or another utility cooling tower which was designed for another utility, but if you are procuring another new compressor which is an air cooled water cooled compressor, so you will in that particular industry, what they do, they connect that particular compressor to that circuit. So both the equipment performance goes on toss, because that particular cooling tower was designed for that particular utility, first utility, and they don't have any spare in that particular. Let's say 300 TR chiller is there, and your cooling tower is around 420 to 450 TR. So your 450 TR was first utilized in your chiller, but now you are adding more load from compressor to that particular cooling tower. Cooling tower does not cannot perform more than 450 TR, because it was designed for 450 TR. So your basin temperature goes on toss. Your basin temperature goes on higher side. So your both performances goes on higher side. Your your chiller also affects, your compressor also affects. So this kind of mistakes do happen in industry. So those are those can be rectified. You can separate out those both the utilities, or you can design a higher cooling tower size. That can be taken as a precaution during during your energy audit or during your designing of any system. So then there is another efficient operation as a pressure settings. We have seen the load pressure and unload pressure. So if you are having a requirement, highest requirement of your system at 6 bar, and your network has a pressure drop of 0.5 bar, so you can set your compressor at 6.5 bar, because your major higher requirement is 6 bar. If you are having good distribution network is designed, you can define your compressor at 6.5 bar. But you have a multiple you can't you cannot set your compressor at 13 bar. You cannot then reduce the pressure at your user end by FRL and all these things methodology, and you are generating pressure at 13 bar and you are using at 6 bar. So you are producing more you are consuming more energy to produce the same amount of compressed air, because they are like throttling the wall at user end. That is an ideal pressure setting has to be there. So if you are having a 0.5 pressure drop and your user has a requirement of 6 bar, you can set your compressor at 6.5 bar. At margin, you can set 6.7, 6.6, 6.7, but you cannot set 8 bar, 10, 9 bar. So your every 1 bar is 6% higher energy consumption. Majorly people in smaller industries, majorly people misconcept your CFM and pressure. To avoid that particular pressure situations or particular pressure mismanagement, you can do the proper networking of your entire distribution system. Then you can do the proper engineering of your distribution network, like what should be a header size, what should be drop size, then how to be design a ring main, so any user cannot affect. So there are general there are multiple industry whenever I do an audit or uh, we see on the field, there are multiple people complaining about we don't get pressure at this much length. We do have a 500-meter circuit, but we don't get pressure at this much. So we have installed another compressor, or we have that particular user has a different compressor. So such kind of energy wastages are there in industry. So how can we tackle those kind of uh, energies? These are some energy saving methodologies, or optimum or efficient use of energy. So if the consider an line where there are 10 users, and the same industry has 1, 2, 3, 4 in single line. So if you are having a header which has the same header is used at to the last user point, so your last user will always get a lower pressure, because during your distribution you are not consider the size of your piping. You have used the same size pipe size, so your pressure would be on same side at every time. So a different pressure, because you are consuming at first point, then second, third, fourth. So your 10th user will always get a lower pressure. To avoid this disaster, you need to design the header size. You need to do a telescopic header or an higher size of pipe should be at first end, then lower has to be there. So this kind of designs can be used, or ring main system can be used. So we need to get a ring main, like this is a ring main. So this is a ring main system. So at any point, whenever your user is consuming air from at any point, you'll get same pressure. But if this system is not, if this is an ideal system, or this is a cut to the system, there's 1 2 3 users are there, let's say 3 users are there. So first will be getting more pressure, second will be get lower pressure, third will get lower pressure. So the pressure drop is there. But if you are using ring main, your this point will be having same pressure. So this kind of circuits can be used as an efficient operation for the air compressed air network. So this is a major challenge in general engineering industry to avoid the cost of piping and all these things. So this kind of networks are not used. So they will avoid the cost of piping, but they will add one more compressor in the system. They will run 2 compressors. From capex, they will spend more in opex. So this is your ideal plant. If this is your plant, so there are compressor modulation or compressor usage of compressor. So you have a 100 CFM compressor and then 200 CFM compressor. So situation is that both the compressor runs, and your 200 CFM compressor is in load unload cycle, and 100 CFM compressor is on continuous operation, continuous loading. So, you need to put your smaller compressor on load unload cycle, because your unload cycle has also, in screw compressor or any compressor, your unload cycle has also energy consumption. You are not delivering any air, but you are consuming energy. So in unload cycles, there is also 30%, almost 30% in energy is consumed. So if we are allowing 100 CFM compressor at base load and 200 CFM compressor as a peak load or on-off kind of thing, your unload power of 200 kilowatt CFM is on higher side. Your requirement is around 230 to let's say 230 CFM is requirement. So 100 kilowatt, 100 CFM is given by this, and 130 is given by this. So your the cycle would be there. Load unload cycle will be there. So what you can do is 200 you can give from this base load. You can set bigger compressor at base load, and the smaller compressor can act as peak load. So this kind of management has to be there in efficient operation of compressor. So this is these are some different efficient operations or energy saving. Those are termed as new as energy saving or energy saving methodologies, but these are some efficient operation of compressors only. So we can see that operate the air compressor at lowest possible pressure. We have seen that whatever your user has a highest pressure requirement, we can do the good engineering, and we can set the compressor outlet pressure near to that particular higher pressure requirement. Then at lowest possible compressor operate compressed air applicants at lowest possible pressure. So if you are having multiple air requirements, like 6 bar is one requirement, then 8 bar is another requirement, 4 bar is another requirement, you can segregate those pressure requirements Four bar requirements is for cleaning, let's say cleaning purpose, and 8 bar is for your any kind of short blasting equipment. So you can separate those two networks and connect those two different compressor to different networks. So those for the surviving that 8 bar, you and yet whatever volume of that 8 bar is on lower side, but pressure is on higher side. So you need to set your compressor at 8 bar, but your 4 bar volume requirement is on higher side. So you are for that 8 bar, your entire volume is generating at 8 bar. So you can segregate those high pressure requirement, low pressure requirements. Then through leakages your energy is like getting drained or getting, we can say, misused. So leakages has to be and continual practice in any plant. Leakages identification, leakage correction has to be in multi regular practice. So we as a company, we have delivered good leakage methodology to reduce the leakages and all these things. So we have given multiple methodologies how can we can reduce the leakages in operating plants. So then any air leakage, like let's say 0.8 mm of orifice size, you are wasting 0.2 kilowatt, and cost of leakage is around 11,000 rupees. You are in a year, you are wasting 11,000 rupees in a year in 0.8 mm leakage. So this leakage reduction has to be a continual process. This has to be a culture in any factory. Then misuse of compressed air has to be stopped in any factory, like body cleaning, then dust removal, then there is like cleaning applications has to be misuse has to be stopped in any industry. Then wherever application can be shifted, so let's say your pressure requirement is one in entire your entire your factory, only one machine requires your 8 bar, and another all factory requires 6 bar. But for that particular machine, we need to generate 8 bar. What we can do, we can generate here at 6 bar, and we can put booster compressor to generate those 6 to 8 bar. So your entire saving, 2 bar saving, can be contributed to energy saving. Then there are multiple for agitation purpose. You don't use compressed air. You can use root blower. Then another is your moisture removal methodology. Whatever we have seen the uh, dryers. Dryers are like majorly there are multiple dryers used. There are refrigeration dryers. Then desiccant dryers are used. Then regenerative dryers are there. Desiccant regenerative. Then heat of compression dryers are there. So nowadays refrigeration dryers and heat of compression dryers are majorly widely used, because this heat of compression dryer, our power consumption is on the very lower side. They use your discharge heat to remove the moisture. And how does moisture from any air can be removed? To if you have to lower the dew point of air. So in heat of compression, we can reduce the dew point, and we can optimally reduce the moisture from the system. So refrigerant and HOC dryers are nowadays popularly used. Then another, likewise, we have initially discussed what is we can use as waste heat recovery to generate more, like generate hot water from the system, and then this particular compressor can be used for generate hot water. Such low quality, like low grade heat, can be converted to hot water, or this heating, water heating, can be avoided with this compressed air system. Then another engineering error is uh, during your designing this compressed air network, your multiple bends, multiple diversions are used. So that particular causes more friction to pass the air, and that will cause your pressure drops across the system. And for that, to overcome that pressure drop, we need to higher the compressor pressure, and that will consume more energy. So that has to be optimally designed. So your entire network pressure drop should not be more than zero point 0.5 bar. Optimum design is 0.2 bar, 0.3 bar, but not more than 5.5 bar. Your pressure will drop, and at whatever length. At whatever length, your optimal pressure drop should not be more than 0.5 bar. Then another energy saving methodology is your usage of variable drive. Variable speed drive. What does variable speed drive do? Like, you have a induction motor in the step, and you are generating rpm, and you are rotating that particular screw element and all these things. So you are generating more air delivery. So you are generating, let's say, 200 CFM, but your plant is requiring 100 CFM only, and that compressor goes in load unload cycle. Your unload cycle should not be more than 30% of your entire cycles. So that continuously going 50% is there. 50% load, 50% unload. So there is a consumption. Let's say 10 kilowatt is your load power, and for 3 kilowatt is your unload power. During an hour, your 5 kilowatt hour is consumed in load, but your 3 kilowatt also, 1.5 kilowatt is also consumed in your unload cycle. So your entire energy consumption will be 6.5, but you are delivering only 5 kilowatt of equivalent of year. So 1.5 kilowatt is wasted. So to avoid that wastage of particular energy, so there can be placement of variable drive. So
Can we use EC motors?
EC motors cannot generate that much amount of torque.
Okay.
Right now, induction motor has to be there because the torque requirements are on the higher side.
Okay. Yeah.
So you can use variable drive. So for that variable drive, you need to give your pressure feedback. Let's say you are at any point of time, given point of time, your plant needs 6 bar. So if we are allowing 6 bar as a load or unload pressure, so that will be in feedback. So if plant require, you are generated 6 bar, you have enough buffer, so you can reduce the pressure, reduce the speed of your motor, and that reduced speed will consume lesser power than your unload. That's how your compressor will always be in load cycle, but at various speeds. The capacity of compressor, so that particular energy consumption of VSD compressor, which will be less than 6.5 kilowatt to deliver the 200 CFM to your plant. That will be, let's say, at there are multiple stages, like five, in general, 5 stages of VSDs are used: 0 to 20, 20 to 40. So these are speed zones are used. So that particular compressor will operate at different speed zones, and that will allow, if you are reducing your speed, so your power drastically goes down, and that uh, affinity laws are there. If you are like reducing the speed of any induction equipment, your power goes by one cube root, goes down by cube root. So these are some energy conservation or optimal usage of air. This is the performance opportunity roadmap. These are all the performance opportunities you can use in your entire compressed air system. So we can go one by one, like type of control system. So if you are using pressure transmitter, so your actual pressure can be more accurate rather than an analog equipment or something like that. So your control system will act more precisely. Your pressure transmitter has to be calibrated. Your control system will be more accurate. You will not be losing that plus or minus 1%, 2% also. Then baselining your system like kW per CFM. kW per CFM of a compressor has to be your baseline. Whatever is your standard operating conditions or standard operating conditions for that particular compressor are there in your compressor. So that is should be in operating conditions also. Then life cycle cost. One is your life cycle cost means if you are purchasing a compressor which has a 0.15 kilowatt per CFM, one model has 0.15 kilowatt per CFM, another model is 0.17 kilowatt per CFM. So they by conscious call, let's say the price of 1.15 kilowatt per CFM is 3 lakh rupees and 0.17 kilowatt per CFM is 2 lakh rupees. You can see that initial capex cost is lower by 33%. But in compressed air system or any in a compressed air system, your OPEX cost would be more than 80%. Your capex would be 10% of your entire life cycle. 80% would be OPEX cost, and another 8 to 10% will be your space and maintenance cost. So if you are allowing 0.17 kilowatt per CFM in your system, you are allowing 0.02 kilowatt per CFM more in your system. So your OPEX cost is going to be on a higher side. That 33% of saving of your capex would be marginal or negligible in the entire life cycle. So that is also opportunity of saving. Then use of recoverable heat is like whatever compressed air system from compressed air system we can use in the form of hot water generate, we can use hot water, all this can be used. Then pressure levels.
Where is the application of the hot water which has been recorded with the waste heat recovery from compressor?
That has to be like during energy audit, there are multiple energy saving opportunities. Like hot water can be generated through compressor. But if there is no use of hot water in your entire plant, what is your use of hot water?
Yeah, because it has to be continuously, because heat recovery is also important from the compressor. Suppose I am recovering the heat from the compressor, that the water is heated at 80 degrees. Suppose I use in the washing machine, for example, and again I have to circulate the water which is again coming at say around 60 degrees. So my compressor will not work because I have to maintain the delta T, inlet and outlet water temperature.
Hmm.
So in that case, it's really difficult because I need to use the water, whatever water generated at the compressor continuously, and I need to feed the fresh water to the compressor. Such application seems to be very difficult in the industries.
No, you can use the higher water flow can be used in the, or lower water can be flow. Flow has to be critical parameter during that heat transfer. In washing machine, in your washing machine application is from automobile industry, let's say, or any forging industry. So your water flow has to be very critical while deciding the system.
Yes.
So that is the main purpose of any energy auditor. Any energy auditor, there are multiple energy saving measures available. There are multiple energy savings in the system can be seen as independent utility. But that particular energy saving, you are generating hot water, but you in your entire plant there is no use of hot water. What is the use of that particular hot water?
Yeah, I mean usage is there, but it is not continuous usage.
Mhm.
Okay, and also I have to feed again the fresh water. Otherwise, my delta T will be not maintained. Suppose in my washing machine, my example as given, because again this water recirculation and delta T, and if it is not recovering that much of the heat, then my compressor performance will again get deteriorated because of the inlet high water temperature, maybe around 55 degrees.
That's where you need to design buffer tank, you need to design good water flow. That is the entire system has to be designed like that.
Okay,
So,
okay. Yes.
that is there was like your in our entire energy audit you can see multiple opportunities, but you need to see as a whole system. You need to design energy saving opportunity as a whole system, not as an equipment. So you like any desuper or any recovery salesperson come and you can buy it from him, but you have to correlate with your usage point, and that is how you can differentiate from other, that we have integrated those both the systems, or we are seeing entire energy saving as an independent, not as an independent equipment, we are seeing as an entire system. Then
Sir, is it possible to recover the heat from this air cooled compressor? Because it has already the heat exchanger that is air cooled. So, is it possible to recover?
yes, it is possible, but not from the air, it from the oil cooler.
Okay.
Pressure levels, different examples we have given. Optimum the pressure drop and all the controlling system pressures. Then misuse of pressures has to be avoided. Then keep equipment in top condition, like maintenance, cleaning of filter, then allowing hot air and all these things has to be in top condition. Then moisture control and air treatment, also we have seen that heat of compression type of dryers, then refrigerant dryers has to be used during your moisture control, because it will consume another energy. Then sizing of receiver is very critical. So whatever size of, let's say there is a thumb rule to define that 1 minute of your let's say whatever meter cube per minute is your delivery of compressor, 1 minute storage has to be there in receiver. The size has to be there for to store the 1 minute air delivery from air compressor. Sizing is very critical. Then multiple buffer tanks has to be there in large scale plants. Then pressure flow control, like calibration of pressure flow control, pressure controller, flow controllers has to be there. Then leakages, air leakages. So we have to avoid the air leakages and bring that air leakages to nil. But that is a regular practice. Then end users, misuse of like inappropriate usage, misuse has to be minimalized. and bring down to zero. And the one more thing is how much air and what quantity, what pressure is much important parameter to define during your compressor selection. Like what is your pressure requirement? 6 bar. What is your air requirement? 20 CFM. Do you require oil free, moisture free? Yes. So your selection of compressor depends on this kind of questions. Then operator experiencing low pressure, such ringmen can be avoid those kind of the designing or engineering of your distribution network can avoid this kind of problems. So this is a performance opportunity roadmap. Apart from this, there are very few opportunities there. And then we are moving to last part of our session is like case studies. One, two, three case studies are there. There, replacement of existing air compressor by energy efficient compressor. Our current specific energy consumption is 0.22. Present day new compressor has a 0.14. 0.08 kilowatt per CFM can be saved upon. For generate 100 CFM, you will require 22 kilowatt. For this compressor, you will require 14 kilowatt. For 100 kilowatt CFM, you will save upon 8 kilowatt. That's the calculation. Around 1.5 year, this much difference can be saved upon. But nowadays, majorly people have shifted from 0.22 kilowatt, 0.20 kilowatt to 0.14, 0.15 kilowatt. Where they have brought new generation compressors and achieved those savings. Then waste heat recovery. Another application is 75 kilowatt compressor.
Sir,
Waste heat
what is the benchmark for this? I mean, kilowatt per CFM for the
lower the kilowatt per CFM is better, always better. There is no benchmark. Everybody claims our compressor is best.
Okay.
You can calculate those for, let's say 15 kilowatt 100 CFM 0.15 is there. Another compressor is saying that for 100 CFM we require 18 kilowatt 0.18 is there. So you can directly correlate those.
Okay.
Waste heat can be recovered from 75 kilowatt compressor, and this kind of fuel can be saved upon. So we'll directly go to question and answers. So these are some energy audit instruments used for energy auditing air compressor. This is a power quality analyzer, then air flow measurement. From air nozzle methodologies, FAD can be calculated. Then sling psychrometer for temperature. Pen type thermometers can be for water cooled air compressors. These are air energy audit instruments. So in the theoretical part, if there are any questions, I can answer those, or we can move to one uh, questions for this particular chapter.
Sir, Rajesh is here.
Yes.
Compressor, they are calculating the FAD, na? FAD P2 minus P1 by P naught. So in that, in question, they are giving the gauge pressures.
Okay.
So same can be converted it into absolute pressure, right? So that
Right.
is
Right.
so sometimes they are using this and sometimes they are not using this. Is it mandatory to convert gauge to absolute or it is not required?
All the pressures has to be in same format.
Either absolute or either gauge.
Whether absolute, whether gauge, all has to be in same format.
Okay, okay. Okay, sir.
Okay, we'll move to one question. There is question bank for energy like in compressed air system. So I'll share this question bank with these organizers so they can share with you. So we'll go by one. Which of the following type does screw compressor belongs to? Screw compressor is a positive displacement compressor. Compressor capacity of you can answer those. I don't need or you can give the explanation why this is so. The compressor capacity of reciprocating compressor is directly proportional to speed of compression. Sorry,
Yeah. Yes, sir. Speed.
speed of compression. The revolution or speed of compressor is important. Then vertical type reciprocating compressor are used in capacity range of 50 to 150 CFM. For higher CFM capacity, horizontal type and slanting type used. The specific power consumption of non-lubricated compressor compared to lubricated type is on higher side because the cooling is not there in non-lubricated. The discharge temperature of two-stage compressor compared to single-stage one is lesser. We have discussed this compression ratio of axial flow compressors are on higher side. The volumetric efficiency of compressor decreases with increase in altitude of place. The ratio of isothermal power to actual measured input power of a compressor is known as isothermal efficiency. The basic function of air dryer in compressor is remove the moisture or remove the moisture in the system. For every 4 degrees Celsius rise in air inlet temperature, the power consumption will increase by 1%. The percentage increase in power consumption of compressor with suction side air filter and with pressure drop of 200 mmc WC is around 2%. 1.6 they have given 250. You can for 250 it is 2% as thumb rule. So for 200 mmWC it will be in lower side. Which statement is true for centrifugal compressor? The compressor should not operate at full load. It is false because the compressors are designed for continual operation. So they are not on load unload type compressors. They are load for full load. They are designed for full load. The compressor should be operated at shut-off pressure. That is the wrong statement because compressor should operate at unload pressure near to unload pressure. The compressor should not be operated with inlet guide vane control. It is false statement. Should be operated with inlet guide vane control because if IGV is not there in the system, your pressure will not be there because it will be from inlet guide vane. You will be generating more velocity and in screw compressor or in centric compressors, your velocity is important. Inlet guide vane gives more velocity. The compressor should not be operated close to surge point. It's right statement because surge point can be lead to higher temperature, higher discharge temperature. Identify the correct statement for air compressor. For every rise in 4 degrees Celsius at inlet air temperature, your consumption goes by 1%. Reduction in delivery pressure of a compressor working at 7 bar, reduction by 1% will give you saving of 6 to 10%. The acceptable pressure drop at farthest point in mains header F1 industrial compressor network is 0.3 bar. So lower the better. Likely estimate on equivalent power wastage of leakage from 7 bar compressed air system through 1.6 mm orifices around 0.8 kilowatt. That needs to be that is an calculations has to be done for this estimate, but for this it is approximately 0.8 kilowatt. From the point of lower specific energy consumption, which of the following compressors are suitable for part load operation? For part load operation, your always two-stage reciprocating compressor is good, because for part load centrifugal compressors will have a worst performance. Then your screw compressor also for part load it will go to load unload. Then two-stage reciprocating compressors will always give a better uh, part load performance. From base load operation and from base load operation and from achieving base specific energy consumption point of view, which of the following compressors are suitable? Nowadays, centrifugal compressors are used for better specific energy consumption, but they are majorly used for higher delivery or higher air requirement. For volumetric efficiency, you do not require power. If the compressor of 200 CFM loads in 10 seconds and unloads in 20 seconds, the air leakage would be 10 divided by 10 plus 20, means 10 divided by 30, 1 by 3. 1 by 3 into 200 is around 66 CFM. So this is the one compressor calculation. Receiver capacity is given as 0.25 meter cube. Initial pressure is 1 kg. Final pressure is 13 kg. Initial temperature 22. Final temperature is 42. Additional hold-up volume is 0.05. Compressor pump-up time is 3.9 meter minute. Calculate the free air delivery. They have given initial and final temperature. So you need to calculate based upon that particular temperature correction. So 13 minus 1 divided by P0 is 1.026 into 0.25 is your hold-up volume, receiver capacity, 0.05 is your additional hold-up divided by 3.9 into 273 plus 22 plus 273 by plus 42. Here FED is 0.837. If the temperatures are not given, you need not to have this formula. This 270, you don't need to add those 273. At same temperatures, you need to calculate on this particular only. Initial P2 minus P1 by P by T.
Sir, sorry, sir. Previous problem, na? As I discussed, they are given the gauge pressures only here. P2 is in gauge only, and P1 is also in gauge pressure only, right?
Okay.
So P0, they have not given. It is atmospheric pressure that we assume is 1.026.
Right.
So here they have not detected the absolute temperature, absolute pressure. Sorry. So 13 minus 1 only they carried out. So that was my query.
So this absolute pressure is P0 is an absolute pressure, na? Right.
P0 is absolute and P2 minus P1 is in gauge only, right?
Okay.
So P2 they didn't convert it. Same as it is they taken.
Just a moment. Just a moment.
13 minus 1 only they taken.
Give me a minute.
Yeah.
Kg per cm square is an absolute. In absolute, you have to take.
Sir, I think difference will remain same. If we calculate now in the gauge pressure, ultimately the difference will be same.
Yes, yes.
13 minus 1.
In that case, if you convert it, denominator will not be there. So
Yeah.
the Same only, sir. Yes.
Same. So that's why.
P2 minus P naught and P1 minus P naught. P naught get cancelled, right?
Yes.
Okay. But this is clear, sir. Pressure is always in same
Same.
terminal.
Entire has to be same.
Units has to be same, right?
Yes. After that, then there is another question. The in automobile industry one, I've already crossed my time. But if you want to have this question, this will be last question. In an automobile industry, one compressor of rated capacity is 1000 CFM is operated to evaluate leakage quantity in the plant during a holiday when no equipment was using compressed air. FED test was also carried out before conducting leakage test and found that the compressor is delivering output of 90% rated capacity. The observation on leakage tests are compressor was on load for 8 minutes, was unloaded for 48 minutes, compressor was consuming 144 kilowatt. So they have given load timing, unload timing, rated capacity, they have given FAD capacity. So in this situation, your compressor rated capacity is 1000, but at FAD it is delivering 90%. So you need to calculate based upon that 90%. So you cannot take 1000 CFM as your uh, year delivery. You need to take as 900 CFM. So operating capacity is 900 CFM because it has derated by 10%. After that, specific energy consumption, you need to calculate specific energy consumption. So your compressor is consuming 144 kilowatt. So 144 kilowatt, 900 kilowatt per CFM. So you specific energy consumption is always in kilowatt per CFM. They have calculated in CFM per kilowatt, but it's on always kilowatt per CFM. So your 144 divided by 900. So it is 0.16. If it would have delivered the 1000 CFM, it would be 0.144. So there is a loss of 0.016 kilowatt per CFM. For 1000 kilowatt, it is around 40.4 kilowatt of loss. Then they have asked us to calculate percentage leakage. So they have given 8 minute load timing, unload timing 48 minute. T upon T by T plus T into 100. 8 divided by 8 plus 48, 56 into 100. Around 14.2% is leakage. Quantity of leakage is 14% into 900 CFM, operating CFM. So means there is around 127.8 CFM as leakage. Power loss due to leakage is around. So power loss due to you have calculated CFM 127.8 and your KW per CFM is 0.16 into 127.8. It's 20.44 kilowatt, 20.45 kilowatt. So this kind of question can be used for your 5 marks questions. So I'll share this document with this team, so you can get it from them.
Yes, sir. Please share this.
Yes, I'll do definitely. So any questions you can connect to me. I'll share my contact. I've already given in the PPT, so you can connect with me. So I can resolve those queries, or you can write to me. Yes. Thank you. Thank you very much.
Thank you, sir.
Thank you, sir.